Welcome everyone to the Caelynx Simulation Success webinar series. Today Carl will be presenting Abaqus Solver speedup strategies. He's going to share with us a whole bunch of ways you can get Abaqus solving as fast as possible, from hardware purchasing decisions to analysis techniques. But before we do that, I'd like to briefly introduce you to Caelynx. Caelynx is a Detroit-based CAE company with engineering centers in the US and Europe and satellite offices across America. We provide simulation services and software to some of the world's top manufacturers across many industries. Our mission is to help companies bring higher quality products to market faster, and we do so while focusing on expertise, communication, and reliability. As engineering consultants, our on-demand CAE expertise is here to serve you from single project analysis to full product development. Our advanced CAE work will help you improve product design, accelerate your timelines, and exceed in-house capacity and capabilities. And we use the latest simulation tools and methodologies to deliver accurate, insightful results so you can achieve greater engineering successes. As a leading partner for Dassault Systèmes Simulia software, we enable companies to do their best engineering with the latest and most competitive simulation tools across a range of engineering disciplines. We are your partner in building a successful digital engineering environment by implementing and mastering CAE technology. Your presenter today is Carl Osterwisch, Caelynx Technical Manager. Carl provides technical mentoring and project leadership at Caelynx and manages our Simulia and FEMFAT support teams. He is a certified Simulia instructor who conducts many of our training classes, and he ably manages our Simulia servers and network. Now, without further ado, Abaqus Solver speedup strategies.
Thanks for that introduction, Zach. Today's topic is Abaqus Solver speedup strategies. To begin with, we'll discuss why solve speed matters, why it's worth the time and effort to understand, and what you can do about it. Next, we'll discuss how other applications and hardware resources can affect performance, and we'll get into specific tips to get the most performance at every step of your simulation process. Finally, we'll conclude with some parting words. So you've set up a model and launched the job on the server, and now what? How long is it going to take before you get the results or discover there's some mistake that you need to correct? When will you be able to review the next steps with your team or your manager? The answers to these questions are important, and often people just accept things the way they are, or they say things like, I can do other things while it solves, or I'll just let it run overnight. Things are working the way they are, so that's good enough, right? Well, hold on. All this waiting around has widespread effects. It slows down the model debugging process, affecting your personal productivity. It occupies a shared server for longer, making your colleagues wait. It reduces iterations per day, potentially bottlenecking the entire development team. It limits concurrent project tracks, affecting business capacity. If you're solving on your desktop machine, then you're going to suffer through some slow performance on other applications. And it establishes a company policy of, well, that's just good enough. These things compound inefficiency on top of inefficiency through the years. So let's get into some solutions. Let's start with the computer you're running on. Abaqus is just one software of many on your machine, and they're all competing for limited resources. If you want Abaqus to run well, then you have to manage the demand, or Abaqus could lose out big at inconvenient times. Many programs love to run things in the background, including self-updates, virus checks, and maintenance duties. In general, that's really convenient, but not while you're running an intense calculation with Abaqus. Beware of background activities like automatic updates and virus scans, and either stop them or schedule them around your solve time. Pre-built computers and Windows 10 itself may come with pre-installed software that's either useless or actively harmful to the stability and performance of the machine, so get rid of that stuff. Some apps are really good at getting themselves out of the way when you're not using them, but you can't rely on that. Web browsers, for example, can take up a surprising amount of RAM, CPU, and even GPU resources in the background while you're doing other things. So close all that stuff down while you're solving. Modern CPUs almost universally have the capability to execute 2 threads per core. This is known as multithreading, and it's commonly understood to mean you basically have double the CPU count. But that's not quite true since it doesn't work with every application. Abaqus is one of those programs that doesn't play well with multithreading. So it's advised that you disable the functionality in BIOS on your solve machine. All other things being equal, leaving it on will probably slow your solve speeds down, potentially by a lot. You may see a minor speed increase if you leave it on and then solve with double your CPUs, as the gray bar shows, but it's a very inefficient use of Abaqus tokens. The temperature of the room where you keep your computer also really matters if you're pushing the limits of performance. When your CPU crunches numbers, it gets hot, and it will slow down or shut down entirely to protect itself from exceeding critical temperature limits. You're going to lose performance without proper cooling. Don't hide your machine in a cramped corner with no airflow, or keep it in direct sunlight or next to a space heater. The form factor has a big influence on computer performance as well. Laptops are very convenient, but they're not really made for number crunching. Even a performance laptop has to put convenience and portability first. They have smaller volume, fewer transistors, more heat, and less performance. Benefits of desktop machines include better cooling, more power draw, leading to better performance, easier maintenance and upgrades, access to higher core counts, CPU speeds, and potentially GPU compute modules. Buying hardware for Abaqus isn't just about flipping through the catalog and picking what hits your price point. Configurations aren't interchangeable, and what's ideal depends greatly on the simulations you'll be running on it. That's where benchmarks like this one are helpful, which compare solver performance for different types and different numbers of CPUs and GPUs on a given analysis. If you send one of your typical models to Caelynx, we can run benchmarks on our equipment and help you decide how to balance your budget against potential solve efficiencies. The right answer may not always be obvious, and it could be very sensitive to your intended use cases. Most obvious example of that would be regarding GPUs. They may give up to 6 times performance improvement for some models, maybe 2 times for others, and sometimes it's no benefit at all. Once you have a general idea of how many cores you're looking for, you may be overwhelmed to learn how many options there are available. This page shows 12 different 16-core CPUs to choose from. The same thing happens with GPUs. If you're looking at the line of NVIDIA Quadro cards, the list is long, and in any given generation, there tends to be only one that will provide the double precision performance required by Abaqus. Beyond CPU and GPU, the system memory has a big influence on performance. Make sure you have enough. If you're running Abaqus standard, the DAT file will tell you how much is required to minimize I/O for the given simulation. If you don't have at least that much, then Abaqus will use scratch space on disk, which is much slower than memory. The benchmarks on the right illustrate the potential performance gap this can cause for a few sizes of models. Ideally, you want Abaqus to solve entirely in RAM, but you still need a fast disk for input files and results. And also the operating system, programs, and active work files are all stored on disk. Solid-state drives, or SSDs, are the fastest by orders of magnitude, but until recently they were very expensive. Solid-state storage is now cheap enough that spinning hard disks should only be used for long-term storage. Beware, there are 2 kinds of SSDs. There's SATA and NVMe, but you definitely want to prefer the NVMe, which is much faster. Try to keep your software up to date. Pay close attention to at least the annual software updates for Abaqus and other Simulia software. Read the release notes in the online manual because you may find new features or capabilities that you'll want to use. For example, expanded implementation of GPU acceleration or other solve speed improvements, new specialized elements or material behaviors, bug fixes, loosened restrictions, life-improving convenience features, and integrations with other software. You can have multiple versions of Abaqus installed at once, so there's little risk of testing the latest release. Now let's talk about the finite element model itself. Automatic tetrameshing seems like a real time saver up front, but it comes at a huge cost down the line. Consider using shell or brick elements wherever possible. They're very accurate and solve far faster than tetras. Shell to solid coupling allows you to have a mostly shell meshed part that turns into 3D elements in areas that require it. In Abaqus CAE, a part could be meshed, could be partitioned and then meshed partly with tet and partly with hex, and Abaqus CAE will automatically tie those incompatible meshes together for you. Abaqus has a lot of advanced element types and material models, but those can come at some cost to performance. So stick with basic types while you're debugging your model, and then add these complexities only as needed. Use a fine mesh density only where it's necessary in areas of interest. The rest of the model can be relatively coarsely meshed. The tet mesh interior growth rate could be adjusted to reduce the size of the model by making larger elements on the interior of the solids, but make sure to check the mesh quality and results when you're doing that. There are many ways that smaller models benefit performance. They require fewer calculations, less memory, less storage, and are also faster to transfer over the network. As another example, it's not always necessary to have solid meshed CAD-accurate bolts. They can often be replaced with beam elements when local details are not important, and that can reduce the model size and improve performance. Adjusting your mesh density in a single model is a common way to control your node count, but that may not always be practical in very large models. So submodeling is a feature that allows you to run a relatively coarse global model for displacements, and then follow it up with one or more ultrafine submodels for high-resolution stress contours in the areas of interest. This is a great way to accomplish things that are impractical or impossible otherwise. With a little creativity, you can incorporate this into other processes like targeted shape optimization on huge models. A lot of designs have symmetrical features and loading. Axisymmetric models are significantly smaller and faster than solid element models for the same level of accuracy. Splitting a model in half or quarters at symmetry planes will also allow you to better focus your available resources on the problem at hand. Advanced features like symmetric model generation can then later be used to extend your initially symmetric model and results into a full model with asymmetric results. Choose the best solver for your task. Abaqus Standard and Explicit can sometimes solve the same problem, but with different levels of efficiency. Standard is a great general purpose solver with vast capabilities for different types of problems, including static equilibrium. Explicit is a true dynamic solver, which can approximate static solutions, and it has advantages for problems with large deformation and lots of contact. But beware that the hardware requirements are different between the two solvers. Within Abaqus Standard, you can choose the default direct or the newer iterative equation solver. The iterative solver may be dramatically faster for extremely large blocky models with many floating point operations per step. However, there are still many restrictions for the use of this solver. Lanczos versus AMS. Lanczos is the traditional feature-rich eigensolver, and it's the default option. But AMS has advantages for large numbers of eigenmodes for systems with many degrees of freedom. and it has access to the GPU for acceleration. Multiple linear load case analysis can be much more efficient than multiple perturbation or even especially general static steps, since there's no iteration required. But multiple load cases may require more memory and disk space. One key to improve solve speed in Abaqus standard is to minimize the total number of iterations. Each iteration requires a certain number of floating point operations, and your hardware is capable of a limited number per second. Each load increment may require many iterations, and if convergence is ultimately unsuccessful in that increment, Abaqus will cut back and start over, so those iterations are essentially wasted. This automatic increment adjustment is a reliable way to achieve convergence, but selecting reasonable initial and maximum increment size may avoid unnecessary iterations. If you set the initial load increment too small, then iterations are wasted just getting up to full load. On the other hand, if you know your model will struggle initially to converge, then don't sit through unnecessary cutbacks by providing too large of an initial increment. If you know your model cuts back later in the step, then don't allow for too large of a maximum increment size. Contact is an extremely nonlinear behavior, and it may cause many severe discontinuity iterations. Consider opportunities to replace contact interfaces with tied constraints. But if contact is required, try to use general contact instead of contact pairs. If it has better convergence, it's much easier to set up using the all exterior option, but you can still optionally include or exclude surfaces or even specify local behaviors and properties. The default contact stiffness may be too high in some problems that have significant bending. You can reduce this with the surface behavior keyword penalty option, which is under the surface interaction. Frictionless contact is simpler to solve and it will converge faster. You may add friction in later steps if needed. The default friction slip tolerance of 0.5% of a typical element size can usually be increased without significantly affecting the stress results. Explicit doesn't perform iterations, so we have to try to minimize the number of time increments in order to improve its performance. If possible, simulate your process running faster. This is not applicable for drop tests or rate-dependent material properties. If simulating a quasi-static event, then make sure that the kinetic energy is significantly smaller than the internal energy, so the inertia forces are low. The stable time increment governs the number of increments for a given simulation time, and it's determined from characteristics of your model that you could control. It's proportional to the element size and material density, inversely proportional to stiffness. You can request the EDT field output variable to see the distribution of stable time increment and ensure that insignificant elements are not dominating the response. Variable mass scaling can be used to increase your stable time increment by artificially increasing the density of the worst elements. This reduces the number of increments, but the additional mass can affect the physics of your problem, so use this carefully to optimize compute speed with minimal impact on accuracy. If you're using mass scaling, you should request EMSF field output to see the distribution of mass scaling, and you can consider maybe remeshing some of those elements with coarser elements. Reuse early load steps as much as possible to avoid duplicating computations or including unnecessary complexity in a multi-part analysis. You can use the same early step and restart from it for different purposes later on. For example, you could have an assembly step followed by different directions of nonlinear loading. Include files can be used to reduce the input file size, and they also could ensure that related models are sharing common features like shared mesh, materials, or steps. Import keyword allows an analysis to evolve from Abaqus standard to explicit or vice versa. Finally, you should always be on the lookout for ways to improve your solve speed. Sometimes the traditional methods you've been using are not optimized, or the software has evolved and you need to take advantage of newer features. A lot of what we do as CAE engineers is repeated methodologies, so if you've come up with a better way, you should share it with your team. And then even small efficiency improvements are multiplicative across multiple projects. You should cultivate an inquisitive and collaborative engineering culture where all the members are seeking improvement together, sharing professional progress with one another, and then the whole business will win. Finally, please don't hesitate to reach out with us if you'd like to improve finite element analysis at your company. We can help in a lot of ways on both personal and company level, like training, certification classes, methodology development, personal mentoring, and more. If you haven't kept up with the latest FEA technology, we can also review your processes and figure out ways to help you stay competitive with your competition. And of course, all of our Simulia customers receive world-class technical support. Thank you.
Now it's question time. Let's start. I noticed that some people had problems with audio and maybe even video. This webinar, after it's done, you should get an email saying you can watch it again on demand. And if that doesn't work, we'll be posting it ourselves maybe later this week. So another question was about the presentation materials. So I actually hadn't thought about a handout or anything. So I'm not sure what we'll do. We might do it as a blog post or make it a downloadable PDF at some point. But you'll always be able to watch the video again too. So Carl, are you there right now?
Yeah. Is my mic still on? Can you hear me?
Yes. Yes.
Okay. Excellent.
Okay. So question time. First question. Is there a way to prioritize whether a token goes toward a physical core or a hyper-threaded core?
That's a good question. Unfortunately, Abaqus itself can't distinguish that. It doesn't know the difference. It's really up to the operating system how the cores are assigned. So if you request all of your hyper-threaded cores, then obviously they'll be assigned doubled up on the CPUs. Hopefully, if you request half of the cores, then the operating system will do the smart thing and distribute the load across the cores. Or what you will find best is if you can disable the hyperthreading altogether.
Yeah, Abaqus, they just kind of say they don't support hyperthreading. It's complicated. It doesn't work for everything, so they just try not to get involved with it at all, and just say just turn it off, which is difficult if you're using the machine for other stuff. But that's where it stands. I mean, you can always benchmark it and see if for your particular problem it makes a big difference or not. But when we benchmarked it, we saw that it did make something of a difference. I imagine it's worse the bigger your model is. Next question, what about AMD CPUs? So Intel has been the only player in server CPUs for a long time. That is not the case anymore. However, Abaqus Standard uses the Intel math kernel library, so until there's some, I assume, substantial changes made to the way Abaqus Standard runs, it'll work better on Intel processors than AMD. However, Intel processors or AMD processors are getting better faster than Intel are. And Abaqus Explicit will not have this problem because it doesn't use the Intel math kernel library. And there is an environment variable that you can change to make AMD CPUs run better in standard. But if you put in a support ticket and you actually have that problem, we can help you out with that. Next question. For Linux cluster conditions, please recommend apps to evaluate the use and identify better configuration and needs.
Is my microphone better right now, Zach?
Yes, it is.
Okay. That's an interesting question. Clusters are very customized. Usually, it's a little bit broad to answer that. But we could run benchmarks on the cluster. We can make general recommendations for memory and network speed, things like that. If you want to get into specifics about scripts, the job scripts themselves, and moving files around, please contact us, and we will we'll help you through that. And you can send email to support@caelynx.com.
Yeah, I would always recommend talking to someone official when you're about to build a new machine, because a lot of stuff that might seem interchangeable may not be, depending on what exact software you're using. So it's always a good idea to ask if you can. All right, next question. At what point with element growth do you feel you lose fidelity in results? I think he was talking about internal TET growth.
Yeah, I think so too. That's a good question. Unfortunately, it's going to be model dependent. So we would recommend that you do sort of a mesh convergence test, as they call it. So you can plot something that you're interested in, such as stress or displacement, and manipulate the mesh and see how that output changes with the manipulation that you do. And then you can evaluate when you've reached some kind of a converged mesh solution.
All right, good question, very good question. Next one, is there a way to know what step size to pick, or is it just guess and check and model dependent?
That's another good question. I'd say, fortunately, Abaqus Standard is very good about automatically cutting back if you've guessed wrong. It will automatically reduce the step size, and as convergence becomes easier, it will automatically increase the step size. And as you go through the same types of models at your company, you may grow to have some experience with how big of a step size you need to have, depending on features of the model, like contact or whatever is in there.
Yeah, I think you can get a pretty good feel for it after a while.
Mm-hmm.
I am running an explicit simulation while defining tie constraints between two edges, but still getting penetration later on. That sounds like a very specific question to their model, kind of.
Yeah, that might be a good example of a support question where we would have to take a look at that. It certainly doesn't sound like what you would expect it to do.
Mm-hmm. So you can contact us. You can see on the screen there's the support contact, so you can email us. And there's also a support request form on the website in the support and tools section. All right. Next question. Hi, Carl. What information does percent change mass show in the STA file?
Yeah, if you're running Abaqus explicit, one of the ways to get the stable time increment higher is to increase the density of the smallest elements. This is automatic mass scaling. So that column in the STA file is letting you know how much more mass has been added to your model using this technique, because any added mass is going to reduce the accuracy of the dynamic part of the model. The inertia forces will go up. So you want to try to keep that low, as low as possible. We have a rule of thumb for if what you're simulating is quasi-static, then you want to stay below 5% is a rule of thumb that's often used. But if that section of the model has a lot of acceleration, then maybe you need to be even lower than that. But that's the idea.
All right. Can you talk about import more? I understand restart, but not the other two. So that was going back to include and import as opposed to restart.
Yeah, include is mainly a keyword that you would use if you were hand editing an input file. It won't come up very often with Abaqus CAE, for example. I think HyperMesh does support it. So that just lets you kind of merge in another input file into your current input file. Like I said in the slides, you can use that for lots of things, like material library that gets brought in every time, or different, if you have the same steps that you have to go through in your history data, that could be an include file as well. Import is very powerful with Abaqus because Abaqus comes with a standard implicit and an explicit solver. So as we said, sometimes it's more convenient to solve a particular step in the analysis using one or the other. You can't mix them in the same model, but import will let you start your model with implicit, for example, tightening bolts in an assembly. And then you can take that final result and import it into an Abaqus explicit analysis and, for example, drop the assembly onto the ground and see, do a dynamic drop test of it and see how it reacts. And you can go the other direction as well for like a metal forming using Abaqus explicit. Could be imported into Abaqus standard to see the spring back and maybe bolted into a bigger assembly, that type of thing. Really powerful feature.
All right, next one. Is Abaqus capable of using the computational power of GeForce GPUs like the 1050 Ti? Okay, so technically it'll run and use it, but it won't do much. So GeForce GPUs, and actually most Quadro GPUs, are single precision compute, while Abaqus is double precision compute. So they are not meant for the purpose of accelerating Abaqus, and they are kind of impeded from doing it. So the answer is basically no. You need a Tesla or generally the flagship model of Quadro. The other Quadros are made for CAD, which is totally different from what Abaqus is trying to do. So you want to look for something that does that has a high double precision compute, which isn't necessarily an easy number to find, but if you're going through the marketing materials for a GPU, an enterprise GPU, you should look for something about HPC and double precision. You won't find it a lot because there aren't a lot of models that do that, but the flagship models are always made for Abaqus, among other double precision applications. Okay, next question. In what way can the Subspace Solver help? Did we actually mention that?
No, that's an analysis procedure. I think that's sort of a specialized procedure, and if you could send me an email to support, we can talk about the application and see how it might be beneficial.
Okay, next question. Is there a list somewhere of NVIDIA graphics cards that support DP math required by Abaqus? There is not a formal list, and it would be a very short list, actually. But there's a site called Tech PowerUp that keeps a database of GPUs. You can just Google like GPU database Tech PowerUp, and they list the single precision, half precision, and double precision of basically every GPU ever made. And if you go in there and you look up Teslas, you'll see like all of them have high double precision. And if you look at Quadros, you'll see the flagship one, which is generally like GP100 or GB100. That'll have a high double precision, but all the others will have much lower by a large factor. But yeah, if you're building a computer and you need to figure out whether you need a GPU, you can contact your VAR like us, and we can talk to you about it, maybe benchmark something for you, because GPUs aren't appropriate for every problem, but when they are appropriate, they're very appropriate. So you definitely want to benchmark your model with a VAR or DS themselves, and then we can help you pick something out. Next question, why do smaller elements and lower density stiffness inputs require shorter time steps and therefore longer compute time? Oh, theoretical question.
Yeah, I can't go too deep into that on the webinar, but it has to do with how fast the wave propagation is across the element. Abaqus, to remain stable, the explicit solver has to have a time increment that is smaller than that amount of time that it would take for the wave to propagate through a given element. So larger elements, it takes a longer time. And higher density, it also takes a longer time.
Good answer. Okay, next question. I also run simulations on a supercomputer. Is it always better to have more CPUs for parallel computation, or is there some sort of setback? So well, I guess I'll start this one.
Okay, go ahead.
It depends on the model size. If you're trying to split a tiny model over 100 CPUs, that's not going to work out because there's overhead for sending data between nodes and negotiating the cores. So there's definitely a limit. It depends on the size of the simulation and probably the nonlinearity and what's actually happening. Abaqus explicit responds better to parallelization than Abaqus standard. Both of them will respond very well to just increasing clock speed, though. That tends to be like a linear gain. But in terms of parallel computation, there's definitely diminishing returns, and you should probably benchmark a representative run of your own and find out for yourself how much of an impact doubling your cores actually does. Oh, there's more to this question. I experienced getting different results using 8 versus 32 versus 84. Yeah, they should be very different. The curve should start to slow down pretty quickly once you get past 16 or so.
Depends on how big the model is.
Yeah, it does depend on how big the model is. Is it possible to estimate optimum number of CPUs required for a job before submitting job to HPC, similar to memory estimate from dat file and data check? As far as I know, no.
No, I'm not aware of any estimate for that either.
Yeah, you kind of got to benchmark once or twice and then use that information going forward, I think. Is it better
Problem
to...
dependent.
Yeah. Hi, is it better to run a parametric study in parallel or divide it into a different model and then run it in one core each?
I think this is getting at maybe running multiple models on the same hardware at the same time.
That's
versus
kind of what it sounded like to me. Yeah.
Versus one model using all the CPUs. Yeah. I think Abaqus doesn't work very well in running multiple models in the same computer because they potentially collide with each other for memory and other resource usage, and
Yeah,
you're going to get better. Yeah.
Yeah, do one at a time. Would it be normal to be getting higher kinetic energy values than total energy values?
No, I don't think that would be normal. That doesn't sound normal. Maybe we can look at that as a support request and take a closer look at.
Yeah. Can import be used with Multithreading and then import that in Abaqus?
Yes, Abaqus supports Multithreading. It's not it's not the import feature as they call it, but there are ways to get the results from Multithreading into Abaqus. You can look for the word Multithreading in the Abaqus documentation or contact us.
Hi, Carl. I am using Abaqus Explicit for the simulation of the manufacturing process. Generally, the manufacturing process would be 2 to 3 seconds long. I cannot use the same time period in Explicit due to computational time. Is there any other alternative to efficiently run the sim with the exact time period as the real process?
Unfortunately, you probably would have to make a coarser mesh or something like that in order to get the stable time increment reasonable. I'd say you can add computer equipment to try to speed up the process otherwise. Mass scaling may help, but like with speeding up the process, you'll have to be aware that the inertia effects might begin to dominate at a certain point. So you have to keep an eye on the results.
Yeah, but yeah, they could review the mesh very closely and see where they can get bigger and then use mass scaling. Is there any estimates for the computation time in explicit/explicit Sulfur versus DOFs? I mean, it's not, I don't think the relationship is that simple. I think it depends on the problem and what Abaqus is actually trying to do.
Yeah, I haven't heard of anything like that. Possibly you could benchmark and get some guidelines for your problems.
And last question, is it okay to have negative total energy in explicit?
I think that might be another good support question that we could review what's going on there.
Mm-hmm. So once again, the support contact is on your screen, support@caelynx.com. And that looks like the end of the questions. So
good questions.
Yeah, it's a lot of them. Good questions. We hope this helped you out, and you'll be able to watch this on demand later. The materials will probably be up in some form at some point. And you can always reach out to us for help. We're always here and happy to help you out. Thank you, and see you next time.